Hello, uh, welcome to this webinar. It's about deep foundations, and I'd like to introduce myself. Uh, my name is Alberto Ortigo, and I'm a geotechnical engineer with lots of years of experience, over 50. I've been a professor of geotechnical engineering for 25 years, and then I formed this company, TerraTech, in which I still work with. And in the last couple of years, I became a fellow of the Institution of Civil Engineers, also a charter engineer by the Engineering Council in the UK, and also a professional engineer in 3 states in America. So I'm going to discuss uh, deep foundation, and let's get started. So the I hope to this webinar is going to last 2 hours, about 2 hours, and within an hour from now, I'm going to make a quick break, 2-3 minutes, and then we start again. So let's go to the what we're going to discuss today. We are going to discuss risks, type of piles, pile selection, and bearing capacity analysis. Okay, so that's the aim of this seminar. And about risks involved, this is an example of two buildings, one, two, three, four, five-story buildings that were tilting due to problems with the foundation. And this is the cause. As you see, the one on the second pointer, yes, this one uh, was built over coarse sand, and of course with the soil with the reasonable bearing capacity. And this one was built on organic clay. So this is the reason. Probably there was not a good site investigation beforehand, and they just copied the
Oh,
design.
better,
Yes,
Professor. Yeah, please
yeah, sure.
share the screen.
Oh dear. Well, it was sharing, but I'll do it again. Sorry about that. Hmm. Can you see now?
Yes.
Okay. That oh, it's not going back. No, it's yes. Sorry. Let's go to the first slide. So this is the first slide presentation, and these are the contents of the seminar that I just spoke about. And this is the risks involved in a very bad foundation design in which these buildings are tilting, especially on the one on the left side. And these are the reasons. As you see here, we have a layer of organic clay, while on the other hand, on the right hand side, you don't have that. So certainly the design was very poor. The foundation design was very poor, and this led to big problems. And this happened some 10, 15 years ago. I've seen this building. And this is something that occurred when I was 1 year old, an accident in São Paulo, and this was very well published in Geotechnique in the UK. And this was a big project by Frankie Pyle. Frankie Pyle, of course, was a big company, a big piling company. And what happens is that they did this is the building, and they investigated these this is the section BB across the borehole. So they had the soft soil, sand, etc., etc., and they didn't have time to investigate this area. Okay, and this is reported in this paper. And then when they did the same type of foundation there, that's what happened in this area. The soft soil here was section AA show the soft soil here is much deeper, and they incurred in lots of problems. It was one of the first cases in the world in which the engineers involved in that building used ground freezing in order to stabilize the building, which was about to fall. And I remember when I was in School of Engineering, one of my professors, who was director of Frankie Pyle, he used to talk about this. And he used, in many situations, he used to ask us, what is the most expensive site investigation type? And I put this question now. We're going to answer this later on. What is the most expensive site investigation type? Okay, this is what happens in the city in São Paulo. As you see, lots of tilting, especially the very tall buildings. They present tilt, as we can see this here, and this has been also very well published in many papers. And this is what happened. They in the beginning they had a kind of sand layer here, which had a very good bearing capacity. It was a dense sand, and then at some stage they had this layer. This is sand. This is sand. This was a layer. It's about 10 meters depth. This sand layer, and then they had this soft clay layer. So in some buildings which were built in the 50s, early 60s, they had shallow foundations, and this led to consolidation and tilting, especially when we had a lot of buildings nearby. They had this problem, and they still they still have present this problem, and there were some of these buildings have been jacked up in order to underpin by jacking. Okay, this is something that happened in Shanghai. Very interesting. This I saw this on the internet some 2-3 years ago, and this was a high-rise building, and they had this excavation close to the piles. And what happened was that this building tilted and fell entirely, as we can see by these photographs that of the time. So this kind of thing we can what we have to do, and we can prevent by proper site investigation, by proper analysis. We won't have these things happening. This is a case. The Shanghai building is certainly something related to the design. They excavate very close to the wall and led to this big problem. Here are some allowed settlements that we should not go beyond some of these values. I'm not going to talk a lot about that, but usually the acceptable differential settlements is about 1/150. If you have up to that, no problem. Usually no cracks. If you're going beyond that, you get some damage to the building. Okay, so let's discuss a little bit of site investigation. What shall we do usually for buildings? These are the type of site investigation that we usually do for buildings. Boreholes, they are very important. Soil rock description with SPTs, which is standard penetration test. CPT, which is the cone quality penetration test. We have to check the water level by means of piezometers. And sometimes if you have, for instance, rock, etc., you have to go into the rock a little bit just to make sure the quality of the rock. Then you have to use rotary drilling. A site visit is absolutely necessary to check about the neighbors, if they have what kind of problems you may have with the neighbors. And you have to check shallow, deep foundations in the neighbors that you have. So, reliability of information. In my life, I have lots of problems related to reliability of information. I'm not going to discuss a lot about that, but usually what we have to do, and this is something that I always ask my clients to do, is to have someone, either the designer or someone else, doing site supervision to make sure that the quality of information that we receive, it's sound, it's good, it's reliable. Also, we can also always save the samples for reclassification afterwards. This is something that we can do. I'm not going to discuss a lot of site investigation, but I'd like to answer that question that I have made before. What is the most expensive site investigation type? And my professors in the School of Engineering used to say the following answer. The most expensive is the one that has not been carried out. That's the one who leads to a lot of accidents and lots of problems. Okay, let's discuss pile types. So there are lots of different pile types, like micro piles, driven piles, bored piles, CFH, which stands for continuous flight auger piles, very much used. There are other type of piles that we're going to discuss here, but usually, of course, the micro piles they can take much less load usually than driven bored piles. Bored piles sometimes the diameter could be like 2 meters, 3 meters in diameter. I have done the larger diameter of piles I have designed in the past was 2.5 meters. Yeah, CFA piles usually up to 1 meter in diameter, not more than that. Okay, so these piles, board piles, are used for very high rise buildings or for bridges, and usually driven piles and micro piles for smaller structures. But we are going to discuss that. So, pile loads. Here we see a typical loading range in meganewtons, and usually, of course, the board piles are those who take maximum enormous load up to say 40 meganewtons, which is a lot. Okay, CFA piles, micro piles are in this range here, less than 10 meganewtons. Driven concrete piles also small capacity piles. Driven steel piles, if you use pipe piles, can be up to 15. Offshore piles are driven, and they can go up to very high loads because they usually go up to 2.2, 2.1 meters in diameter. And of course, screw piles, which I'm going to talk late today, those who take much less load. In terms of diameter, this is more or less what we have. These board piles I've told you can go up to 4. I've never seen this. The max I have done was 2.5, but they can go up to 4, definitely. And usually CFA piles up to 1.2 meters, not more than that. Driven concrete piles, most piles I have done in the past, they were not large as 1 meter. They were less, much less than that, up 0.8 centimeters, 0.8 meters, etc. And driven steel, they can go up to offshore piles. They go up to 2.5 meters in diameter. And this pile depth, if you're going to very, very deep, say beyond 40, 60 meters, you have to go to board piles usually. And why? Because that's the equipment, the only equipment that goes so deep. And usually driven piles up to 60 meters, not more than that. Micro piles, of course, the CFA piles much less, maximum usually 30 meters. Steel screw also not limited depth. So we have to divide the type of piles between shaft friction piles, are those who take a lot of friction along the shaft, so they are known as shaft friction piles, and of course end bearing piles. If the tip reaches a very hard stratum, and then it can take a lot of tip resistance. So this is a tip resistant pile. We have to classify piles according to this. Let's talk initially about precast concrete piles. Very common for a small building. Very common for a small building. Okay. See here, different types from different manufacturers. This is just a catalog showing the different types. And here we have the manufacturer, and we have square, we have round, hexagonal, etc., cross, etc., etc. We have all these types. And when we start a project, you have to, if you're going to use a concrete pipe, you have to contact the manufacturer and get the properties of these manufacturers and organize a table like this. That's the type of table that I organized for this particular manufacturer. So we have the outside diameter, wall thickness, concrete section, tip areas, etc. These are data that we're going to use in for the design to select the pile size. Okay. Let's review how we install reinforced concrete piles. Here are some examples. These concrete piles are more or less 50 centimeters square, and usually we put marks on the pile in order to count the number of blows that are needed to drive these piles. And then we have the driving. This is a kind of diesel hammer. We're going to discuss hammers very soon. And this is how we install these piles. And this is raising the pile. You have to do very carefully. Usually you have to pay attention to the prescription from the manufacturer, how to handle and raise the pile in order to avoid damage to the pile. They can break if you do it wrongly. And here you raise, you prepare for installation. Then there's the case of splices. They are different. Every manufacturer has a different type of splice. They are, for instance, one of the most common for spun piles, this type of splice, in which we have welds. And usually the precast centrifugally spun concrete pile is by far the best. Why? Because usually we get very high concrete strength. For instance, I've worked with piles with 50 megapascal up to 80 megapascals. Some recent jobs I have done with this pile that the strength of concrete was very high, and this makes installation much easier. And why? Because installation of concrete pile is a problem that we're going to discuss, because if you apply a lot of energy, you may break the pile in tension, as we're going to discuss later on. And this is a kind of catalog for one of these precast centrifuge concrete pile, and spun, and this allows structural load and compression and tension, pile diameter, etc., etc., etc. From a catalog like this, you can choose, once you have the load, you can choose type of pile that you're going to use. And here, one of my first projects, I was very young. I did this big project. It was in Brazil a long time ago. And so lots of concrete piles, and I was involved in this construction. And this is me, long time ago, observing and a pilot test that was being carried out there. Okay, so how do I? This is the power installation that I'd like to. I think I have to. Oh dear. Okay. So this is an installation with a freeform hammer. And one of the disadvantages of the concrete piles are the losses. We get about usually 10%, usually I consider 10 to 20% of losses when I compare the cost of this pile with steel piles. Usually concrete piles are cheaper than steel piles, but they are much more difficult to install. And also they have this advantage of losses that have to be taken into account. Okay, this handling concrete piles very carefully in another project which I've been involved. This is the hammer. We're going to discuss this. And then what you have to do before you install a pile, you have to do quality control. And usually you have to look for cracks because these are very common. During transport, during handling, you may crack the piles if you don't do it properly. And then usually what you have to you measure with a device like that, with a template like that, you measure the width of the crack. And if it's over 1 millimeter, that's the kind of criterion that I use. Over 1 millimeter, I refuse the pile. This is an example of very bad handling which I've seen in the past. And these people, instead of handling these piles with a winch, they just put at the end of the truck, they put a kind of ladder and roll the pile down to the bottom. And this led to cracks that I've seen. So some of these piles which I was working on at that time. This was a very old project, some 30 years ago. We had to refuse. This is a very old and simple drop hammer, and we're going to discuss other hammers afterwards. This kind of crack that we may have, okay, and if you have to measure the width of the crack, and my criterion is to refuse all piles if we have more than 1 millimeter. Example of cracks, these are vertical cracks, and a pile like this should be refused, okay? These are damaged piles during driving. Of course, this can you have to cut this off, but the pile itself may be accepted if the stresses are not too high. We're going to talk about that. And concrete piles, as a summary, they are more economical than steel piles. We have to do pile quality check, absolutely necessary. You have to drive them slowly. Why? Otherwise, you may damage the pile. So you have to do much more careful driving of these piles, careful handling to avoid cracks. Okay, and check driving stresses. This can be done by dynamic pile testing that we're going to discuss. Of course, you have to do pile load tests in order to check whether the pile is okay or not in relation to the design loads. Okay, and this is different types of concrete pile tests that you can carry out: ultrasound, electrical resistivity, Schmidt hammer. This to test the concrete before you install the piles. I have a project in which we did all these tests in order to check the quality of concrete, because in the beginning we didn't trust very much. And then once the pile is installed, you can do a dynamic pile test. We're going to talk about that. Mobilization for a static test and static compression test, absolutely necessary. Lateral load test if you have high lateral loads, and tensile load test if you have, of course, tensile loads, tensile design loads. Let's talk now about steel piles. Steel piles, you can use H section usually, or pile piles, okay? They are very easy to handle. They can sustain high tensile driving stresses, and this is very important. This is what makes steel piles much easier to drive. There, and also corrosion. That's the only problem you may have. This could be addressed by, usually what we do, I do, is to discount 1.5 millimeters around the perimeter of the pile, and by doing that, we may not have any problem. Can be filled to concrete if necessary. Okay, open. We can use open or closed-end pile. I'm going to talk about that. And pile stick-ups be cut and reused. This is a big advantage in relation to concrete piles in which the stick-ups cannot be used. However, you have to do it carefully, otherwise you may incur in damage the piles like this one. This is an H kind of section was damaged by heavy hammering. Okay. Also, you have to find your supplier of steel supplier, and find the catalogs. And for instance, this well-known manufacturer, they make H steel piles, and I have used that a lot in the past. And this one of the projects is a factory for the British company Rolls-Royce, and we did a lot of piling. There were soft soils, and then piles were very, I don't remember, we were the designers, but piles could be 20, 25 meters deep. And this was a very successful project. And here are people doing the dynamic pile testing. Okay. This was a recent development that I have seen from this company, Tupper. Tupper is a steel manufacturer, and they develop, they make these steel piles. But what they did, which was very good, they developed this kind of inserts or pile coupler, okay, in which goes into the pile, and then you just give a blow and it works. It works very well in compression, and I have used this a lot. And why? Because we don't have to do welding. And welding, if you are going to weld the pile, it takes 1 hour usually to do it properly. And then you have to check the quality of the weld, etc., etc. And this pile doesn't need that. They have developed 2 diameters. One is 240 millimeters in diameter. The other one is 273. Wall thickness is 8 and 9 millimeters here. And I have used this pile very, very successfully. We're still using this pile in a very big project in Guyana, in Georgetown, in Guyana. And this has been very successful. As I'd like to show you here how. That's it. You don't have to weld. This is a major advantage because you save 1 hour work. And these different types of welding, if you're going to do tensile stresses, tensile loads, you have to design tensile load. Then you have to weld. And these are different types of welding that you may have. Either you just weld the connection, or you use these plates in order to transfer the tensile loads from one section to the other. And the other thing that you have to consider, whether you have open versus closed-ended piles. Usually for very long piles, you don't need to close the ends, okay? You can test for that, but usually when you have a very long pile, use open-ended. And what you have here is the pile plug. is the soil plug that enters the pile, and then it behaves like it was closed. And this usually for deep piles, let's say 20, 30 meters depth, it's very good, and I've used that a lot. Also, offshore piles, which I've designed in many years ago, the very large diameter piles, we don't close the end as well. They are always driven open-ended. Okay, so pipe piles are very easy to drive. And here's an example on a project I have done in the Amazon River. The city of Manaus in 1985 was a refinery, Amazon refinery. In those days, we did what was my one of the first time I have done PDA, dynamic pile testing. These are very old equipment, and these were the piles. They were about, I don't remember, something like 1 meter in diameter, and it was a very successful project. However, if you apply a lot of stresses during driving, you can damage the pile. How do you avoid damage the pile? Usually, you have to limit the maximum stresses. And how you measure these stresses? By doing a dynamic test on the pile. Usually, the first pile that you drive, you measure, you do the PDA test, dynamic pile testing, and then you check for the maximum stresses on steel piles and concrete piles. Usually, the steel pile, that's the advantage. You can go easily up to 90% of the strength of steel. And in most, the steel that I have used in the past, they are about 350 megapascals, so it's safe to go up to 300, okay? Either in compression or in tension. While concrete piles, the maximum compression that you can apply usually is the FCK. I've shown you that those centrifuged piles, they go up to 80 megapascals. But in tension, you cannot apply more than 10% of FCK. Otherwise, you're going to generate cracks. You're going to damage the piles. So, also, I have used in the past also old rails. This is not very common, but sometimes old rails can be effectively used. Usually, they are given free of charge by old railway companies, and I have used old rails as well as foundations in a few projects. Not many, but in a few projects. Let's have a look at the hammer selection. How do I select a hammer for a particular project? Okay, here are the types of hammers that we use. Hammer type: drop hammer, which is very simple, diesel hammer, hydraulic hammer, and here the vibratory hammer. Okay, and how do I select those? Drop hammer, the advantage, simplicity, minimal mechanical parts, cost effective, low mobilization costs and operational costs. Versatility, can be used on small scale projects. But the other disadvantage, and which are the slow rate, very low frequency of blows. Okay, so if it's a small project, that's okay, but it's a large project, do not use this. Pile damage, high risk of damage pile head, especially in concrete piles. And inconsistency of energy delivery varies during the project. So small projects, okay, large projects, no way. Diesel hammers, they have this following advantage. The self-sustain requires no external power packs, as the hydraulic one, which I'm going to talk. High energy, excellent for driving piles into hard soils. Durability, well suited for heavy duty projects. Large projects, you can use that. Disadvantage, Environmental impact: smoke, potential oil leakage, lots of smoke or lots of potential oil leakage, and extremely loud. So in a city center environment, no way you may not use this kind of hammer because the neighbors are going to complain a lot. And sometimes they have problems or hard to start in soft soil. Takes some time to start giving operating this kind of hammer. The hydraulic hammer, it's excellent, but we have to adjust. You can adjust the stroke length and energy. If in soft soils where diesel hammer might fail, you can use this hydraulic hammer. It's cleaner and quieter, much more environment friendly than the diesel one. And disadvantage: a lot of cost. It costs a lot of money. Requires specialized maintenance. And the power pack, you must have a power pack. Hoses add significant weight. Okay, but usually is one of the best hammers that you can use in a project. And finally, vibratory hammer. Advantage: significantly faster than impact hammers. Can be used for both driving, extracting piles. That's very important. I have, for instance, used this for sheet piling. And I remember one of the projects, there was a mistake. The sheet piles went too deep and we have to pull it out, 30 centimeters on each pile. And this was done very quickly with one of those vibratory hammers. It generates constant vibrations, so low impact noise. Disadvantage: in effect, in very stiff clays or rocks, work best in non-cohesive soils. But one of the most important disadvantages is no set measurement. Usually, you use the number of blows in the final drive of the pile to measure. That's what we call the set. What the displacement per blow in the end. This way of controlling, of quality control of the pile, and you can't use the vibratory hammer for that. I have used in the past. Usually, in that project I've shown you from Rolls-Royce, we used two hammers, one to drive a vibratory hammer to drive the pile, and another hydraulic hammer that came just after it to measure the set. This was very important. Hammer selection. How do you select the hammer? The rule of thumb, usually the hammer weight is 2% of the design loads. Okay, example. So if you have a steel pile, the design load is 2,500 kilonewtons. The hammer weight should be at least 50 kilonewtons, not more than that. Okay. The other thing that which I do a lot is to talk to the manufacturer or to talk to the contractor. Usually I use their experience in order to select a hammer. These are different kind of hammers, for example, gravity, diesel, hydraulic for particular loads. And then you have here, just a second. Oh, here. No. Sorry. Okay. So we have here for each load the type of hammer that you should use. These are kind of, this comes in pile manufacturers' catalogs, and I use this, but mainly I talk to contractors. This is very important. I use their experience. You can do a drivability analysis. Of course you can. And this is what I'm going to show you now. But usually I rely more on experience rather than drivability analysis. I have done this drivability analysis a lot, especially for offshore work in the past. How do you do this kind of drivability analysis? You use a kind of theory that was created in the 60s by a guy, an American guy called Smith, and he developed this kind of wave equation analysis in which here's the pile, the hammer, here's the ram, here's the block, steel block that received the blow, the pile cap and things like that. And he models the pile with a system of springs and lumped masses and dampers and carries out a numerical, one-dimensional numerical analysis of the wave equation. I'm not going into details, but this is very common. And I used to, in the 80s, when I was working on offshore piles, I did a lot of drivability analysis using a wave equation program, which was in Fortran in those days. And this is a kind of output that we had. For instance, here is the strength at the time of driving in meganewtons, and here's the blow per meters. And this wave equation gives me, we enter the characteristics of the pile, of the soils, etc. And they give me these kind of curves for different types of hammer. And then we can select the hammer for the strength of the resistance of the pile during the time of driving. And this is the strength of the pile during the time of driving that we estimated through static methods, which I'm going to show you later. And here you have the pile depth, the strength, and which hammer we could select either D30 or D44 in order to drive these piles. Do I use this today? I can use, but usually I don't. Why? Because I rely mainly on the experience, and also we can do this modern program called GRL Leap. This program we can also simulate. This is a kind of simulation that we have done for some piles. This is the strength at the time of resistance, pile resistance at the time of driving, maximum stresses and energy in kilojoules. And here, from these simulation, here simulate this, the pile was a 340 millimeter pile, and this was the selected hammer, and we managed to simulate this and find that this hammer was capable of driving this pile. But what I do today I prefer to rely on experience. Usually I can do this kind of analysis, but I prefer to rely on experience and then to do a pile dynamic test in the beginning, in the first piles, in order to check the stresses, driving stresses, etc., and pile capacity. Okay, let's go to Franke pile. Franke pile was developed in Belgium by this guy named Franke, probably in the 30s, I'm not sure when. But there was a very, very common type of pile in the past. Perhaps today, much less. And what they usually do, usually we drive a casing to the depth of the pile, the steel casing, to the depth that we need. Then you pour some concrete here, and you have a hammer, a drop hammer, in which you give blows to the concrete until you form what we call the bulb or the tip, okay? And then you install the cage, the reinforcing steel bars, cage, and we use the same hammer to drive blows to the pile as we extract the steel casing. And this was very, very common, especially I think in the 70s, and today a little less. And for instance, from the Franke catalog, these are the diameters they used to do from, say, 300 to 700 millimeters. and the maximum allowable structural load in compression and tension. So the maximum allowable structural load for this 700 millimeter pile is 2,600 kilonewtons, and tension only 500. Okay, so this kind of updated version of Ferrari pile, in which they don't have the bulb, but they use a modern equipment to do it very fast. I remember one of the old equipment that I've seen, the 70s, when I started working, they use about 10 people. So it's an intense labor type of pile. So that's why today this kind of pile is not very much used as was in the past. A very common type of pile, very effective, very economical, is the continuous flight auger pile, the CFA. Usually, what you do, you drill using a thread, an auger, kind of auger, okay? Then you pump concrete as you pull out the flight auger, okay? Then you install the reinforcements, and the part is ready to go. Here are some photographs, CFA pile installation, this continuous flight auger. Here are some photographs of installation. These piles were say 20 something meters in depth, okay? And this is the steel reinforcement installation. Usually these piles are very difficult. If you have a long pile, sometimes it's difficult to install reinforcement down to the end. And then you do in the first 6 meters. This is the case in which, as you see, the tip of the reinforcement is bent a little bit inwards, and there are these rollers to facilitate the installation of the reinforcement. These are the rollers or spacers, okay, which facilitate the installation of the reinforcement. Here's how the reinforcement was installed, and this is something which I don't like very much, is to put some load on the cage in order to press it down. Some manufacturers, some contractors, they have a vibrator, which is much better. This is the way which I don't like. I like the use of a vibrator instead. And this is more or less kind of diameter that we can have, usually from 350 to 1200 millimeters. These are the most common diameters, but the most common diameters are from 400 to 700 millimeters. Usually, if you keep for normal buildings, if you keep within this range, you have the lowest price for installation. If you go beyond that, usually the price starts to go up. And why? Because there's much less equipment available, at least where I have been working on. And these are the kind of loads that you can apply from 800 to 2400 kilonewtons. You have to ask your manufacturer this kind of table and use this. This kind of pile has a strong limitation in very soft soils. If you have very soft soil, usually more than 5 meters deep, okay, thick, more than 5 meters thick, you may not use this kind of pile. Why? Because of possibility of damage. When you're extracting the auger, you may have the borehole may collapse or may cave in a little bit, and then this pile should not be used in soils with SPTN less than 4 meters, especially if the thickness of the layer is over 5 meters. Okay. This manufacturer, CZM is well manufactured. Yeah, friends of mine, and they have a big factory in America. And this is the maximum length, they go up to 35 meters, usually the mast, because this depends on the mast. And they have this kind of equipment, which is very good, has a very strong torque over 200 kilonewton. Usually, this is the kind of equipment that I like to specify because these ensure that's going to enter in reasonable hard layers without being refused. These are normal specs that I use for CFA piles. Cement content, usually over 400 kilonewtons per cubic meter. Slump minimum 22 centimeters. Maximum water cement ratio 0.6. Aggregator sand and pea gravel. Grout content 55%. Mixed design has to be done by a specialist, but mix design, the design has to be the mix has to be designed to be pumped, and strength usually over 20 megasparks. I like 30, but that's the minimum. Okay, CFA pile installation. You have to do monitoring. Why? To make sure for quality control, and then some new rigs, they have this pile installation monitoring system, and they measure the volume control, concrete pressure, torque, rotation, speed, shaft dimension, and they generate one report with plots like this for every pile. What's the advantage of this? You have to look at especially the pile profile. This is the most important one, in order to check if there is any kind of defect to the pile. Okay, if the borehole is very common in soft soils, when you strike the auger, you may have a borehole collapse and you may have a damaged pile. So you have to look at that. This is very, very important to do this kind of quality check. Okay, and these are what I'm showing, the two flaws that took place. Not a big damage. Why? Because the concrete pressure dropped a lot here, and as the concrete pressure dropped, we may have a reduction in the diameter. This is a problem, and what you have to do if you have something like this, to do additional pile tests in order to check the integrity of this part. Okay, these are CFA piles in soft soil. You have a very, as you see here, very low pressure when you are extracting. They did maintain the pressure, and there was a reduction in the diameter as well. Okay, this is another one in which you have a drop in the concrete pressure, and you may have a drop in the diameter as well. So, and now let's discuss a little bit of bored piles. Bored piles are usually for very large loads and very deep. Okay, what you do, you have you put a temporary casing. Usually, if you have a soft soil here, you use a temporary casing here, install. Okay, then you go on drilling, and you stabilize the borehole with drilling fluid. We're going to discuss this kind of drilling fluid. Can be bentonite, or today much better, polymer. I'm going to discuss this later on. Okay, and then you can go very deep. For instance, I have just done a project which I'm going to show later on, the Demerara Bridge project in Georgetown, Guyana, and the piles were almost 100 meters deep. Then when you when the piles are driven, you install the casing with a winch. Okay, and then you start pouring concrete, but using this Tremie pipe. It's a pipe that goes down, and you start pouring the concrete from bottom upwards. Okay, while the mud is being pressed away. Okay, this how it's being a series of slides how we do that. So we drill, we install a casing like that at the top, varies according to the strength of the soil. Then you go to the pit, the tip, install the casing, and then you pour the concrete from bottom upwards. And then you have the pod ready. Why to use polymers instead of bentonite? Most of my projects until say 10 years ago, we used bentonite. That was the normal material. Then some companies like this one, GEO, they came up with the idea of using polymer instead. And we found polymer much better. Why? First of all, in the past, some countries they have regulation in which bentonite, once we use, they are not environmentally friendly, and they have to be transported far away for discards. On the other hand, polymers, no, they are biodegradable. They are very environment friendly. So we can cut this cost of transporting the bentonite mud to discharge to a landfill or something like that. The other thing, the other very important characteristics, they can allow admixtures to improve the quality, to increase viscosity, to facilitate descent, and most of all, it's much cheaper. It's about 70% less than 70% of the cost of using bentonite. So when we discovered this kind of polymers, I never used in my projects bentonite anymore, just this. And these are some characteristics of the polymer. Why they behave so well. They kind of develop a membrane in contact with the soil, which is better than those developed by the bentonite. And so the advantage, polymer is biodegradable. This cut a lot of costs. Polymer saves concrete. Usually you have a reduction, say 5 to 10% maximum. Easier to descend, to take the sand out, to clean the fluid, and more important of all, more economical than bentonite. So I once I discovered this, I never use bentonite anymore. Boarded pods. This is a typical catalog. You can have boarded pods say from 600 millimeters, these up to 2,000 millimeters. Maximum I have done was 2.2 or 2.5. But there are some cases in which equipment can go up to 4 meters. I never done that before, but it's possible. Okay, and this the tip area, perimeter, stiffness, and allow to structural load from 1,400 kilonewtons to 15,000 kilonewtons. Okay, so 15 meganewtons. So very large diameter. Usually, what we do, we calculate the capacity in relation to FCK with the unreinforced concrete of 5 megapascal. This is the usual value. Some standards allow to go up to 6. I prefer to keep it safe with 5. That's my experience. That works. Oh, so here's some. I have worked in Hong Kong very long ago in 1996, and here's my name in Chinese, which is Onpato, which I'm very proud of to have a Chinese name. But in Hong Kong in those days, they did a lot of building, high-rise building. They were 35, usually 35 stories building. And some of the projects which I visited, they were these caissons, foundations, hand excavations. And here, very interesting. Usually this kind of company, small company that used to excavate these caissons belonged to a family. So the wife operates the winch, and the husband is down there excavating the material. So I visited a few projects with this. Also, some of the projects I have been to, they had this uh, board pile diameter up to 3 meters, and this is one of the projects which I have been to, and they have huge equipment to bore or to drill these piles in. This is a 3 meter diameter, and that's me, Hong Kong, in 1996, long ago. Well, before we go into Demerara Bridge, I'll make a break, 2 minutes break. Let's start in 2 minutes, okay? Okay, well, I'm going to discuss this project, which was a major project that I have been involved in the last 3, 4 years, was the Demerara Bridge Foundation. I'll show you. This is the location. This is Guyana in South America, and this Demerara River, and this is the bridge, which is a very long bridge. It's about 3.2 kilometers, and this is the part, the main part, and the total length is 3.4 kilometers, the total length. The west approach is 1.3 kilometers long with 34 piers, P naught to P33. The main span 570 meters, P33 to P36, and the east approach 900 meters long with 27 piers, P36 to P62. For this bridge, the standard to be applicable to the design and construction was the AASHTO standard, RFD bridge design specs that we had to follow. And what kind of soils that we have there? The geology, no? We have usually in that area what they call Demerara Formation, which the thickness is usually from 10 to 40 meters in depth, and this is a very soft clay. Then you have Pleistocene Coropina Formation, the depth vary from 6 to 25 meters, is a stiff clay. And why? Because it was over-consolidated in the past. Due to erosion, it became over-consolidated. And then we also have the Pliocene white sand series. This varies a lot, from 30 meters thickness to 1,000. They are what we call the white dense sands. And this project was undertaken by the Chinese company CRCC, and we became consultants to them in order to follow up the site investigation and to do all the geotechnical analysis. And it was a very interesting and very successful project that finalized last year. The bridge was inaugurated, I think, October last year. I have some information about that. Then the soil profile. So what we see here, the Demerara formation is very small. Usually doesn't appear because here we have depth up to 100 meters. And why? Because the piles were to be very long in this formation. And this, what we have here is the clay, the Coropina formation, and the white sands were interlaid there. Okay, and these are some properties of these clays in which we had hundreds of soils, hundreds of tests, unit weights of about 20 kilonewtons, 19 kilonewtons per cubic meter. Here, water content in the average was about 35, 40, usually. Plastic limits, they are not the high plus some of the material that presented high plasticity of 60. Okay, the plastic limit is about 20%, and the plasticity index of these clays varies from say 20 to 40%. We also carried out some seismic CPTs, and the CPTs were very good to detect the change between in between the Demerara and Coropina formation. So these are soft clay, recent clays, and these are the over-consolidated clays, which show a very clear separation between them. Okay, so we carried out some CPTs, and they were very, very useful. The undrenched strength of these clays, the Demerara, which is the recent clay, usually we had a value of about say 15 to 20 kPa on drainage strength. But if you go, so this for the Demerara clay, but for the Coropina formation, the strength is much higher, up to usually 150 kilopascals. So a big difference between the Demerara and the Coropina formation. So we had to analyze the piles according to the Astro method of analysis, which is prescribed in these standards. So how we do that? We input the data, usually the N value from SPT, soil type, and pile dimensions. Okay, and then you calculate the stress and energy correction to reduce the SPT value to a standard 6% energy. And in clays, this is a very common method. We asked to prescribe the use of alpha method, which is undrained method, in which you calculate the undrained strength using correlation like this, 8 times the value of any being the correct SPT. Also, you can calculate the unit shaft friction, okay? And we have limits. The Astro method prescribed limits to the unit tip resistant Q, which has to be less than 4 megapascals. And if where we have sands, okay, what we do, we use the beta method, which is the factor stress method, in which we calculate the unit shaft friction with a correlation like that, but it has to be less than 200 kPa. That's the limit. We calculate then the unit tip resistance using a formula like that, 60 times N60, and it has to be limited to 3 megapascals. And then we integrate along the depth, and we calculate the total shaft friction, the tip resistance. Then you calculate the total factored resistance, which different values of factor of safety applies, and you have to take into account all details about how the method applies. Also, there are other methods which we decided to use, and some of them were very good. And CPTU, that's by far the best method, the best correlations, the best method for calculating the power capacity based on CPT. However, we couldn't use that. Why? Because CPT didn't go very deep. They went up to, say, 30 meters or so, but we had points that reached nearly 100 meters. So we had to use SPT methods. And these are the most common methods that I have used in the past. This one was the correlation with N60, which I just have shown you. However, we had a lot of experience with these methods based on SPT with uncorrected values of SPT. Why do you have that? Because in the 60s, the early 50s, my professor at school, both Aoki and Veloso, they were, Dr. Veloso was technical director of Frankie Pine, and Aoki was the deputy director, and both were my professor at school, and they started to develop correlation between SPTs and the behavior of points. And then other people like this DQ Quaresma, other researchers did something similar. And finally, this friend of mine, Paulo Frederico Monteiro, he was also became later the technical director of Frankie. He improved the method, improved the correlations, and this what I've been using almost all my life. So, however, and this was a program that I helped people from GeoLogsMiki. GeoLogsMiki is a company, is a Greek company, and they do very good software that I use. One of them is CPT. They do the SPI. They do the PMT, which is for pressure meter analysis, and they do lots of geotechnical software. And these guys are my friends, and we developed together. I helped them to develop this SPI, which is based on these correlations. So this is very simple. I used to do it with a spreadsheet. Now I use the software. It's easier and faster. So we can the unit tip resistance is a function of NSPT, and these are empirical coefficients. Unit shaft friction is the same. We have this N from SPT, alpha and K and F2 are empirical coefficients. And these are the coefficients that are inbuilt in this program. If anyone can, this program costs very little money. I don't know the price, but it should be kind of $100 or so. But it's very simple, very straightforward, makes very beautiful plots. And I've been using this program for some time. And these are these coefficients for different types of piles and different types of soils. Okay, so this is CPT profile. This is the best method in which, if you have a CPT profile, you can calculate the barrier capacity through the LPC, Laboratoire Ponchaussee, the French method, which was developed in published in 1982 by two researchers of the Laboratoire de Ponchaussee in France, Bustamante and Gianezzi. This is by far is the best method. However, this in this case could not be used because we have a limited depth of the CPT. Then we use the AASHTO method and we use SPI. Okay, SPI produces this kind of plots in which here you have the SPT's values, okay, type of soils with different colors, and these, for instance, these for 1.5 diameter bored pile, we came up to the conclusion that the length would be 75 meters for the design loads. Okay, the spine also furnished this kind of plot, which is N. This is the Q, tip resistance, shaft friction, and this is the bearing capacity plot. Okay, for the shaft and shaft plus tip. As you see here, the tip has only say 10%, maximum 10% of the shaft resistance, which is good. Here the same kind of plot for the AASHTO bearing capacity for this kind of pile. Here you have the N. Here the drain strength obtained by correlation. And this is friction value for sands, shaft friction, Q, tip resistance, and here you have the allowable bearing capacity. This is total, this is shaft. And then we have been ordered to use the AASHTO method, which we did, but we managed to compare the S-pile, in which we have 30, 40 years of experience, with AASHTO. And the results were about the same. We're very happy with that, that the results were about the same. And we could, at least check by two of these methods the plots, and they gave almost the same results. This is how the piles were built. This is the steel casing, which was locally built for these piles, and they went throughout the Demerara clay, and this is how the reinforcement was being built, reinforcement cage. This is myself, one of the visits that I paid to the site, and for the installation, the contractor decided to build this temporary access trestle, okay, the trestle bridge as well, for the piles to be installed like this in this kind of scheme. They installed the casing with the vibratory hammer, and they then this is the pile steel casing, just for the upper part of the pile. Okay, then they use a drill rig to drill throughout the pile depth, and then they poured the concrete with a Tremie pipe. Here's the Tremie pipe, this is the winch. Okay, some picture of the construction, pile installation. This is a vibratory hammer, and this is something which first time I've seen this equipment. I have been working with many contractors, and they always had a piling rig with a mast. And this was the first time I've seen a wireline pile drill rig capable of reaching very deep depth. And this is only 6 meters in height, but it's a wireline. Let's see how it works. As you see here, it's only 6 meters. So these pipes, they transmit the torque to the drill bit, and this is the drill bit which was used there. These are very, very interesting Chinese equipment, which I haven't seen that before. And then the Chinese carried out bi-directional load tests. There's something very interesting about this test. which was invented by a fellow countryman. His name was Pedro Elísio. He's about 10 years older than I am. He was a very good friend of mine. And he started the first experiments of these pilot tests with a hydraulic cell. Instead of applying the load to the top of the pipe, he decided to insert a hydraulic cell in the middle of the pipe, and then the tip would react against the upper part of the pipe. And when you're dealing with very large diameter pipes, it's impossible to carry out a pilot test. The cost is too much. And then this guy started to develop something like that and carry out his first test in a place called Nova Lima in Minas Gerais, state of Minas Gerais in Brazil, in 1961, so long ago. In 1983, he wrote a book. It came in Portuguese and English as well, and he gave me one of the books long ago. However, at some stage, Pedro met Professor Osterberg in America, and Professor Osterberg was very interested in this kind of tests, and Pedro sold some 500 of those hydraulic cells to Load Tests Incorporated, the company that belonged to Professor Osterberg. But in 1984, Professor Osterberg applied for a US patent, okay? And Pedro was forgotten in this patent, although he was the one who developed the test. And this is one of the projects I work with him. Pedro is here. He's still alive, but he's not working anymore. He has Alzheimer's, unfortunately. But I'd like to I'm saying this to, praise the memory of Pedro Elísio, who did this. And these were the cells that he developed. This was in 2014, and this is the kind of test that he used to do. And the Chinese did that, okay? But with another company. The test setup and loading. So what they had, these are the piles, and these are the cells. They had two cells. One operated initially, okay? First, they put pressure in the lower cell. Then they open the lower cell, and then the upper cell as well. Okay, this is the upper cell. And then they close the lower cell and then load the upper cell. So they carried out 3 pile load tests with this technique that was originally developed by Pedro Elísio, a friend of mine. And this was the pile test to the 1.2 meter diameter test. Okay, as you see here, this is approximately the capacity. Then up to this value, loading meganewtons is about 20 something. Soon after the load, the displacement increased a lot, so we can consider the capacity to be this value. And here was the design. As you see, it's much safer. Also, the maximum displacement is less than 5% of the diameter, which is also a criterion for you to accept the pile. So this pile was very good. The next pile, 1.8 meters in diameter, also the design value was about half of the capacity, so the results were very good. And this is the 2.2 meters, the largest diameter pile that was carried out in this project, which were designed. And as you see, the design load and capacity, it's about 1.8, which is okay as well. So I managed to compare the prediction versus measured results. As you see here, the green is the predicted by the AASTO method, the red is the measured, and the blue is the SPI, the method that I used before. So what we see are very close values, And the design value was this, and the measure was that. So we have a very, very good result. This pile was 1.2 meters in diameter, 75 meters depth. These are the 1.8 meters diameter pile. The results are the same. Very good prediction between both methods, S-pile and the Astro method. And here's the measured in red, okay? And this is the largest one. This pile was nearly 90 meter, 95 meters depth. As you see, the tip varies a lot, but the shaft is okay. That's the prediction. That's the total. And this is the prediction by both method and the design. As you see, factor of safety was very good. So the factor of safety, according to the diameter, is 3, 2, 1.7. So in my view, all of them totally acceptable. And this is the bridge after it was inaugurated. It was inaugurated in October last year, and a very successful project. Okay. Let's talk a little bit about micropiles now. Micropiles are usually for small loads, not very high loads, but sometimes when you have rock, for instance, if you have boulders in the soil profile, micropiles are very important because they can be drilled through boulders, through rock. Also, if you have, for instance, soft material or loose sand, and then you have rock, you can pin all the micropiles into rock very easily. Okay, so they are very helpful, usually for small to medium projects. Let's have a look at micropile installation. So that's it. You drill, you install the reinforcements, and you can grout as well. So these are typical pile diameter, usually from 100 to 450 millimeters. The most piles I have done in the past, they are 300, 400 millimeters in diameter, okay? And this is the maximum allowed structural load, usually 1,000 or 300 kilonewtons. Usually these are the sort of load capacity I use for these piles. And it is an example of project. One of the projects, I have been involved in many projects like that, in which we carried out drilling, reinforcement installation. Reinforcement can be normal with several rebars, or sometimes you use a kind of DiviDag threaded bars. And these are some examples of the project that I have done. Housing project, usually this case here, I think they were 6-story building or 4-story building in the city of Petropolis. And this another project I have done. Different projects with micropiles. Nothing very fancy about micropiles. Let's discuss screw piles. Screw piles, well, I've been using in a few projects, and they are main application underpinning, transmission towers, pipeline foundation, industrial floors, and soil anchors. Sometimes they can be very, very helpful. So these are different types of screw piles. You can use a solid square bar with this helix. Solid square grouted, can be grouted pipes as well if you want to grout. Can be hollow pipe grouted, okay, or just hollow pipe without grouting. They can be very useful for some applications like pipeline anchor. If you have an uplift, this could be a way of, ensuring it's not going to float. The pipeline is not going to float. And this is a kind of characteristic from these pipe catalogs. You have the diameter here in millimeters, and here you have the thickness, and usually the tube diameter. Of course, any design could be different, but this gives an idea: maximum tensile load and maximum compression load on these parts. So, as you see, they are very good for tensile load, and that's why they are very much used for transmission towers. They can be stored in very confined space. I have done this in, for instance, an existing airport. I might have a photograph of that, in which the design was with micropiles, and I replaced it by screw piles. The advantage was very quick and very small space. So they can be the equipment necessary is very small, just a hydraulic excavator like that. We replace the excavator, the bucket, by a motor, a hydraulic motor, and then you can store the pile. So we always use a torque cell. I'm going to show you. By using this torque cell, we measure the torque, and this is a way to control, for doing quality control. This, as you see, this is a very small equipment, also can be used for installation, okay? We can do in very limited space, and also can be used for underpinning. When you have settlements, you can underpin easily with this kind of pile. Can be used on tiebacks as well. Usually, the advantage of this pile that you can store and remove afterwards. Okay, now a temporary tieback can be used, and here's kind of underpinning. Then you have to use this kind of bracket to support the foundation of the building. These are kind of brackets for underpinning that could be used easily. And here, some bearing capacity analysis. You can do how to analyze this kind of pile. You can analyze individual support. If you have this the spacing in between these screws have to be over 3 times the diameter, these 5 times, in order for one not to interact with the other one. Okay. Also, you can do an analysis of the surrounding cylinder. You have to do both. Okay. The individual support method, you use an equation like this, in which the Q is the ultimate load, soil cohesion, effective vascular stress at the helix depth, gamma is soil unit weight, D helix diameter, helix area, and these are bearing capacity factors that depend on phi, on friction, soil friction, then can be obtained through graphs, and there are programs that we can use as well. Individual support method, you just use something like this in clays, and this is the helix area, soil cohesion, times 9, a very straightforward bearing capacity analysis. If you have sands, use something like this. This is the area, Q, effective vascular stress at the helix depth, and the bearing capacity factor, also can be obtaining plots or graphs or charts or even calculation. And also, you should always use the surrounding cylinder method, in which an equation like that applies. Very very straightforward, the bearing capacity equation. And I'm not going to all details, but I have shown you that before. And also, we have always to check the maximum torque method, which is a quality control method during installation. As I have shown, you measure the torque in kilonewtons, and then the torque in kilonewtons meter, you multiply by an empirical factor to get the ultimate load. And there are lots of prescription about what kind of K should be used in different soils, etc., etc. I'm not going to go into details, but and this is here is an equation that could be easily used in order to calculate the K with this kind of equation as a function of the helix diameter. This works, okay? And you might be concerned about corrosion, and then there are ways of doing that. One of them is to do hot dip galvanizing, and sometimes it is used for soil anchors. Epoxy painting, there's another way on the exposed parts that you have to take into consideration. And now we're going to discuss how site investigation affects the foundation design decision. Okay, this is one of projects which I've been involved. It's a big tower, some 40-story, and one of the things that happened was this was the initial borehole that I received, and this showed soft clay here, and we carried out some design based on this. What happens that I asked for a confirmatory soil boring after, and then when I received the results, they were quite different, especially in this part. As you see here, we have a very soft clay with N equal to nil, okay? And here we had uh, uh, a low value of N, or SPTN, but still value were about 4, 5. Let me check. Yes, they were about 4, 5. So this makes a big difference. And why? In such a case here, I would never design the CFA part, which could be the cheaper solution for this project. I design driven piles. And why? Because if you have deep soft clays, that's for small loads, that's the way to go. However, when I received this pile, okay, I could design something totally different, which was CFA pile, which was much cheaper. Okay, so this is how the quality of an example of the poor results that I received before, which led me to a very conservative design, and then I could improve the design when I received this borehole log. This is another example. If you have a borehole log like this, you have here medium gray sand clay, stiff to hard clay silt, and then hard residual soil. What kind of foundation could we apply to a borehole like this, a borehole log like this? There are several types. One of them is to design a short Franke pile. If you have Franke pile bearing on this hard residual soil, that's going to be a very good solution. There are other possibilities, like depending on the load, you can do if it's a bridge, for instance, with a very high load, you can do board piles, but then you have to go into this hard layer, which sometimes is not easy to install the pile. So here, driven piles out of question, CFA piles out of question, micro piles, yes, micro piles could be used in this borehole because we can install the micro piles by drilling in this hard residual soil. Let's go ahead a little bit. This is another project, and what kind of pile I used here? I used in this project was a bridge. The loads were not very, it was not a very big bridge. And then what I used was micropiles. Why? Because I wanted them tipped in this very hard material. And something which is missing here is if I have a profile like that, I always have to do some, because this was just SPTs and we didn't have rotary drilling here, just wash boring. And I asked we ordered a few boreholes entering into this very hard material with rotary drilling in order to confirm the quality of this material. And this is this project that we used micropiles. Okay. This is a project in Georgetown that took place a few months ago. Georgetown, Guyana. Guyana is, as you see here, very soft clays. Okay, it's a local company that did this borehole. They did a lot of tests, etc. And here's the SPT. What happens here? What's happened here that they stopped the SPT at a very low value. The SPT was stopped when it reached 4, which is absolutely not acceptable. We had to go at least to 30 with 3 measurements. Usually what I specify, you can stop the borehole after you have at least 3 measurements, consecutive measurements of SPT over 30. Okay. And here is a quiz, but I'm going to do it together. In the quiz that you may have received, you may have other examples. What kind of pile types for medium loads or building loads I would design in such a profile? Definitely, I would go to CFA, continuous flight auger piles. And why? Cheaper than driven. I would not use driven piles in a project like this. Okay. This here you have a very soft soil, as you see, n equal to 0, nil, and then it goes up a little bit to 22, no, 32, and then it drops to 12, 8, 9, etc., etc. It goes up again. What kind of pile can I use in a project like this? Driven, definitely. Because you have a lot of soft soil, and then the most adaptable or the best type of part for the product like this for small loads. What I mean small load. Normal builds up to 10 story, 20 story, etc. Usually, I would use driven piles in a project like this. Okay, the driven piles they can be 20 meters. Here's let's say he's about 80 meters. So these piles would be say 15, 20 meters deep. Another very similar profile, soil profile, and then you have what you have here up to 8 meters. You have very soft soils, and then you have, it looks like here we have two boreholes together, 1, 2, and then what you have here is if you have 80 meters of soft soil, no way you have to use driven piles. This is project. What was this? Okay. This is a project. You have soft soils and then gravel and then sand, some residual soil, and then you have rock. So, which kind of pile can you use here? If you're dealing with small loads, small buildings, definitely it has to be driven piles because of the soft clay. You cannot use, you can use micro piles because you can go through the soft clay and leave a case in the soft clay. And all the micro piles, you can drill into the rock. You may have a socket. Also, you can have here, if you're dealing with kind of a bridge too large, you can do bored piles, but you may have to go with bored piles, you may have to go into the rock. And drilling a socket for bored piles in rock is not cheap. Okay, so either micro piles or bored piles for large loads. Finally, I'd like to address excavation in soft ground for casting the pile. This is sometimes forgotten, and I've seen along my life some disasters that took place, some accidents that took place, not catastrophic catastrophic accidents, but small accidents that should not occur if the design was proper. This is a kind of a project that I've done long ago for the Brazilian underground in 1994, in which the piles were properly designed, but the excavation was not well designed. And what happened was nearly a big failure took place, so they have to redo all these piles and the losses, but they have to redo that. And this is something which I've seen long ago. I was consultant to the client, to the owner, the Brazilian underground system, and I advised them not to use those piles because they have moved with this displacement. Some of these piles, especially here, they have moved. This is another project that I also was consultant. I told them to, before they start excavation, and I told them not to do that without proper design for the excavation. And because there were soft clays and embankment soft clays, when they start excavating, some of these piles, they tilted like this one. So they have to be replaced. Okay? So my recommendation is that all these piles, they should be, all these pile blocks, they have to be proper an excavation design in order to avoid horizontal displacement of the soil close to the piles. And finally, I'm not going to go into a lot of details in this seminar. Perhaps we may have another seminar to discuss pile testing. I'm just going to discuss briefly what kind of tests that we have to do. All concrete piles, they will have to do concrete tests in order to analyze the slump, so workability, check. Compression tests, 7 and 28 days to check strength, the concrete strength. Usually, they are, according to specs, you have, in most cases, you must be above 20 megapascals. Some of the specs that we use today go even beyond that, up to 30 megapascals or megapascals, sorry. Here, we have some of the tests that we carry out when to check the behavior of the pile after installation. One of them is the pile integrity test. We do a lot of that. It's a low strain test. Why a low strain? Because we hit the pile with a hammer, and here we have an accelerometer. When we hit the pile with the hammer, the wave goes down there and reflects. And if there is a defect or damage of a reduction in the diameter of the pile, we are going to know that because there will be a lot of reflection. So ways of analyzing the pile and accepting or not accepting the piles. We do a lot. And we always specify in concrete piles mainly to do in all piles to check for defects. The board piles, which I have shown you, we always do cross-hole sonic tests. This test is to check also for the defects in the concrete. We have these access pipes pre-installed in the cage. We have done a lot of those tests. Usually when the pipe is 2 meters, every 30 centimeters in diameter, we put one additional pipe. The minimum would be 4, the maximum could be 8 if the diameter is over 2 meters, okay? And then we do sonic tests in order to check defect. It's a wave that goes from one tube to the other. One is the emitter, the other is the receiver, and then we check the quality of concrete for large diameter piles. The most common test is a static compression test, in which we use a jack and we have a load cell, and we measure the pile displacement with dial gauges here. One important aspect of this kind of test is that we should never measure the loads through the jack or through the hydraulic jack. We should always use an electrical load cell. And why? Because when we start the tests, we may have friction on the jack piston, and this leads to errors up to 30% of the load. So I never accept that loads are measured with the hydraulic jack, although there are some standards that may accept that. I don't accept it at all. Then this is the static compression load test, the most important test for compression loads, in which we test the pile for small loads up to 5,000 kilonewtons. 5 meganewtons is very, very common. So we can do also a static tension load test. While if you have considerable tensile design loads, you should do the tension load test. You can do lateral load tests when you have high lateral loads on the piles. And we do a lot of dynamic load tests, the PDA. What's the advantage of that? We measure the stresses during driving. This for pile driving is very good because we measure the amount of stresses, the tensile stress, the compression stress, and then we check whether or not the driving and the hammer is operating well and it's not damaging the pile. Of course, there is the expansion load cell, which is not covered here, but I've shown you before. So these are the pile testing. I have another seminar that I might give some time in which we're going to discuss all these tests in more detail with examples. Okay, so it's nearly 2 hours since we started, and that's the end. And I'm available to answer any questions that you might have. Of course, I thank you very much for your attention, and I hope you can benefit from these, you could benefit from this discussion. Okay, thank you, and I'm ready to, if there are questions, I'm ready to answer. Okay. Yes. Thank you very much. There are no questions, so thank you very much for your attention. You can, if you need to contact me, you can contact Insight with this email that's there, or I'm always on the other side of the line. Okay. Thank you very much. See you next time.